Thank you for the invitation, and I am afraid I'm not talking about non-regular things, so my spacetimes are going to be smooth. I hope this is okay. And so I am going to give you a talk about this thing that I call ultramassive spacetimes, and this is the outline. I will devote some time to some introduction, and in principle, I think this will be enough because I will tell you everything I want to tell you in the introduction. And then I will go to some terminology and the toy models that I built some time ago. And then I will try to explain that these toy models somehow have some uniqueness properties. And they are, in this sense, they are universal properties. Now, the main point I want to make is that when there is a positive cosmological constant, there is an extra, you have an extra constant in your space-times. So you have like an extra length, in this case, an extra area, which is fundamental. And then this may give you some limits. And in particular, we know that the lambda, the cosmological constant, puts a limit on the area of trapped surfaces. And the point I want to make is that this limit is not really a limit. And if you have black holes which have an area very close to the limit, you can produce things which are even bigger and that they are more powerful than black holes, actually. Right, so let me start by saying that, well, we somehow know that there is a kind of a cosmological constant which is positive due to observations. So we have to rethink everything we know in general relativity about that, taking into account that lambda is positive. And a particular known result that comes from 1994 is that the area of marginally trapped surfaces, well, I will always call surfaces, but they are always closed. And in principle, they only have to be outer trapped. They have a limit, which is given by that, where G is the genus of the two surfaces. Now, marginally outer trapped surfaces are defined by a mean curvature vector, which is null and consistently pointing along the same null direction everywhere. And this is what I'm going to call the outer or the external direction. And they are said to be stable if, when you perturb them in that direction, they become untrapped. Now, this stability assumption, when it is considered in the spatial directions, is usually interpreted as that these trapped surfaces or marginally trapped surfaces are enclosed in a black hole region. So this is the intuitive idea. Now, to understand these limitations, I consider some simple spherical symmetric models because I had a problem in my mind. You see, if you have a spherically symmetric, say, black hole, and you have a cosmological constant, we know that the area of the marginally trapped surfaces increases with the mass. And then I wonder what happens if a black hole information is very, very close to the area, but then I keep sending more mass. What is going to stop this so that the marginally trapped surface cannot increase anymore in area? This was puzzling me. And then I showed that actually the spherically symmetric dynamical horizon, so the hypersurface that is foliated by marginally trapped surfaces, merges with a timelike membrane. So this is the same idea, but instead of being a space-like, it's timelike. And they merge at a distinguished round sphere, which has the maximum allowed area, and where these two things change, forming a marginally trapped tube, which changes signature precisely there. Okay, we'll show you some nice Penrose diagrams or conformal diagrams with these toy models. Now, this entire hypersurface, which is space-like with a portion of dynamical horizon and a portion which is a timelike membrane, is a marginally trapped tube, and I call it a generalized holographic screen because this concept of holographic screen was introduced by Boso and Engelhardt. But the things we find is a little bit more general. And this satisfies an area law. So the area increases when you go along it in a particular way. So there is something which is more powerful than black holes, and these things emerge. And when physicists are asked, so what is the ultimate fate of things that are collapsing? And then they say, well, there are neutron stars, and then there are black holes, and this is the end. Well, in my opinion, this is not the end. There is something even more powerful than black holes. Now, future infinity fully disappears in these models. There is no future infinity at all. And instead, what you have is a universal singularity in the future. And the space-time becomes like a contracted universe. So, given that the area of the marginally trapped surfaces in these models goes beyond the limit, I call them ultramassive, because in spherical symmetry, this means that they have more mass than the maximum mass allowed. And then when I build the models, I thought, are these just particular things, or how can I look at them, because they are with spherical symmetry? So now I have been able to prove that these properties are somehow universal. So if in any space-time where you approach this bound of the area for marginally trapped surfaces that are stable in space-like gyrations, then the following properties always arise. They develop these marginally trapped tubes, which are generalized holographic screens with this topology. They satisfy an area law, and they always contain a distinguished marginally trapped surface, which is stable in a null direction, with constant Gaussian curvature, which is precisely lambda, and that's of maximal area. And then all possible marginally trapped tubes that pass through this distinguished surface change signature precisely there. Now, a future singularity arises, and there is no black hole, but something which is different, and I will show you what it is. Now, there is an exception to this situation, which is generic. And this exception is given by spacetimes that are foliated by killing horizons or things like that. Yes, so I have a space-like hypersurface. This can be a space-like, timelike, or null. It changes from one to. Okay, so now some basic notion. Oh yeah. Well, the definition I'm using is the standard one. So you have a future null infinity. You take the boundary of the past, and this will be the event horizon. There is no future null infinity. That's the point. You will see the picture. There is no future null infinity. So there is no question of calling it a black hole. So I am just giving you some basic notations and terminology. Probably all of you know this, so I will be very quick. So my spacetime is four-dimensional with this signature. I assume Einstein field equations with lambda, which I assume also positive. The energy momentum tensor satisfies the dominant energy condition. S will denote always a space-like compact surface. And this is the first fundamental form. These are the tangent and the normal vector fields on S. And in particular, I will choose two null vector fields, which are normal to the surface. I will call them L and K with this normalization. This is it is standard. And of course, the covariant derivative in your spacetime can be decomposed. This is the intrinsic derivative on the surface. D and K is the second fundamental form, or the shape tensor. It depends which literature you read. And of course, this is by definition normal. And then it can be split into the total shear tensor, which is the trace-free part, and of course, the mean curvature vector, which is normal. So this is the important object, H. Now, of course, given that this is normal, you can always decompose it along the two normal null vectors. So these are called the second fundamental forms along L and K, the shear along L and K, and the expansions along L and K. And these are obvious definitions. Now, The causal character of the mean curvature vector determines whether your surface is untrapped or trapped or marginally trapped or something else. So the important things that interest us today is that, of course, if there is no mean curvature vector, this is called extremal. It could be minimal or maximal, no expansions. If it is null and points along one of the two directions, then these are called mods, or marginally outer trapped surfaces. In that case, but the second expansion is negative, this is a marginally trapped surface. If both are negative or H is timelike future, then this is a trapped surface. So in what follows, I will use mods. They are like this, okay? Or marginally trapped surfaces, which are the same plus the second expansion negative, which is the same as saying that H is future pointing everywhere. But this is also standard, so I hope that this is not a problem. And then last thing about terminology, a marginally outer trapped tube is a hypersurface which is foliated by one of these mods or MTS. So if this hypersurface is space-like, it's called a dynamical horizon, also a fourth or future outer trapped horizon. It depends on the literature. And if they are time-like, they are called time-like membranes, also future inner trapping horizons. In general, they don't have to be of any of these two kinds, and they can change signature. And if there are null portions, and if these null portions of the hypersurface point along H, these are zones where the marginal trapped tube becomes a non-expanding horizon. And then in the original definition of holographic screens, these portions were absent, but I am going to allow them because they are very important in the physics of these things. So this is, I will consider the general case. Okay, so far this is the introduction. So now I'm going to the toy models. So this is the fun part of the talk. I'm going to use a very, very simple spacetime, which is called the Vaidya de Sitter metric. So this is the Vaidya metric. So this is like the partial solution with, instead of a constant m, a function m which depends on retarded time. So sorry, advanced time. So v is advanced time. And then there is lambda. So this is the standard round sphere metric with unit area, sorry, unit radius. R is the usual areal coordinate. So the area of the two spheres is 4 pi r squared. V is advanced time, and these are the range of the coordinates. Now, this spacetime is a solution of Einstein field equations with lambda for this energy momentum tensor. So this is the derivative of the mass function. This is called the mass function, by the way, with respect to V, and then this is the null vector arising in here. This satisfies, sorry, so this somehow represents, this is sometimes called null dust. So this represents null particles coming into the space-time in a spherical manner. So you have to imagine null particles coming to a center, something like this. And this satisfies the dominant energy condition as long as the derivative of the mass function is non-negative. So it's a very simple model. And I will also assume that this function m is always non-negative everywhere. Now, if this is a constant, this is called the Cutler metric, or also spatially de Sitter in the literature. Now, in particular, if the mass is 0, this is a portion of de Sitter. Now, round spheres, so round spheres are given by V and R equals constant, are marginally trapped surfaces whenever this happens. And this has real positive solutions for R, given a value, a concrete value of V, as long as this happens. Otherwise, there are no solutions, or otherwise there are no marginally trapped surfaces. Denoting such the solutions of this equation, if they exist by R plus and R minus of V, because they depend on V, you always have this particular, I don't know how to say, inequalities. So R minus is always less or equal than the inverse of the square root of lambda. R plus is always greater, but there is a maximum limit for R plus. Also, as long as V increases, which is the same as saying that the mass increases, because I am assuming that M is an increasing function, this R minus tends to the 1 over square root of lambda, while R plus goes back, so it decreases toward the same value. In particular, they can be equal only if there is a value of V, which I'm going to call V bar, which is this, okay? So this is the limit here, the equality. If this happens, the two solutions coincide, and they are equal to 1 over square root of lambda. Okay, so now the idea is very simple. I'm going to take a model where the mass function is 0 until V is 0. So this is the zeta. V is advanced time, so the zeta. Then at a given time, I will put some mass function, which is increasing, and then I will stop at a given value of V1. And the final value, I'm going to call it mu. So that will be like the total mass of your spacetime. Now I interpolate between the 0 and mu with the function, any function, which is just non-decreasing, okay? And now there are basically two possibilities. Either there is a value of V bar here in this interval between 0 and V1, where you reach the extreme case or not. These are the two possibilities. This is the same as saying that the final mass, or the final mu, is either less than this value or greater than that. These are the two possibilities. And then I will show you some conformal diagrams. So this is the standard situation that most physicists have in mind when they think of a collapse like this with lambda. So this is scribe minus, past null infinity, and all this region below V equals 0 is the zeta. Okay. Now at a given V, these null particles or flow of infalling radiation starts coming in. So this is the shadowed region until V is V1. And then this is a mass, so this will be Schwarzschild-de-Sitter, or more properly, Cutler. So from V1 there, this is always the Cutler spacetime. Right. So when these infalling particles reach the center, they produce a black hole. And then in particular, there is a dynamical horizon. So I remind you, this is a hypersurface foliated by marginally trapped surfaces. In this case, they are round spheres, which is space-like, and this dh here. And then this dh merges with the event horizon, because now we have a future null infinity, scribe plus here. This blue region is like a cosmological de Sitter region in the sense that there are trapped surfaces, but they are past trapped surfaces, so h point to the past. And by the standard definition of a black hole, this is the event horizon. So this is the boundary of the past of null infinity. Right. So the dynamical horizon emerges there. So there is nothing new here. This is the standard picture. You can see it in many books and many papers. And then this extension goes forever because you can extend Cutler Metric infinitely to the right. Now, when I put here red, I mean that these are the zones with future trap surfaces. So future trap surfaces are above the edge and to the right of this line here. And also, yes, that's it. Now, in the Sitter, you know that there are this kind of horizon, cosmological horizon, and this merges when the mass comes. This becomes a timelike membrane, so this is timelike, and it's foliated by marginally trapped surfaces, and then again merges with the R plus of Cutler, but with the mass mu, okay? This is a different value. I don't know if this is understood, but this is a standard. So this is a standard black hole with positive lambda. The point here is that this value of V is less than what I call V bar, or if you want that the total mass, mu, is less than 1 over 9 times lambda. What happens if this is not the case? So the picture completely changes. This is the picture. Now the idea is the same. I have the Sitter, Then I throw null particles. The dynamical horizon starts, but you see, it never goes to merge with anything which is an even horizon, because there is no future null infinity. If you look up, this is a singularity everywhere. By the way, this space-time is globally hyperbolic. There is no problem in that sense. Now, the dynamical horizon and the previous thing that was a timelike membrane, they merge. They merge precisely at the round sphere, which has the maximum allowed area. Okay, so this point here represents a marginally trapped surface, which is stable in the null direction, and that has a maximum area 4 pi over lambda. And here you see the dynamical horizon, which is a space-like all the way, becomes null there, and then it becomes time-like, and then again null. Now this entire thing is a marginally trapped tube, and this is what an example of a generalized holographic screen. And there is an area law. If you follow this direction, which by the way is the external direction all the time, the area is always non-decreasing. Okay. Now, from this line to the right, this is the Cutler metric again, but now with a mass which is larger than 1 over square root of lambda and 3, something like that. You see there is no future null infinity, no question about any event horizon. There is no event horizon anywhere. So given the standard definition, you cannot call this a black hole. And you can play with this picture for a long time, but take this observer here. This O here, it starts at past null infinity and it ends in the singularity. Now, if you take the past null cone of this guy, he will never, ever, ever see anything like a marginally trapped surface or the mass which is infalling or anything like that. He's just living in a collapsing universe and ends up in a future singularity. But these things are happening on the other side of the world, okay? Okay, so this is an example of an ultramassive space-time. This is the basic one. But let me show you another one, which is even more interesting. It's the same idea, yes. This? No, this is just an effect of the conformal picture. I mean, I can also draw it like this, and then as long as this keeps a space-like, it will be okay. It was just to fit it in my. So this is the thing you can do with conformal diagrams. You can play that. But the important thing is that this is a space-like everywhere, and this is also a space-like everywhere. And by the way, that point is not part of the diagram. Okay, this is my next example. This is a little bit more funny. Why? Because so this is the same thing, the sitter, then I send mass, there is a dynamical horizon, which merges with something which is null. Then I stop sending the mass. And then I wait for a while, and then I send even more infalling null particles after a while. And then again, this thing becomes a dynamical horizon, and this becomes a timelike membrane, and they will again merge at this particular surface with maximum area. What is interesting about this diagram? Well, if you compare this diagram with the original one, everywhere below this line V equals V3 is exactly equal with a region if you cut this like that. So this is the thing that it was going to be, you see the event horizon. Yes.
Minus is supposed to be null boundary, right?
Yes.
And this should be
Yes.
so real spacetime is some product over this.
Oh yes.
This is a subset of R11, but then I don't understand it.
But some basics about conformal diagrams. In spherical symmetry, the conformal diagram that you plot is the the non-spherical part, then you have to multiply by S2. So in this sense, every point is a sphere. Okay? Except now, about whether this is finite. This is a conformal diagram. So this is not finite at all. This is past infinity. So this is infinitely in the past.
Still, I mean, the compactness past boundary of this. What would come about and how it should come.
This is not compact. This is the point. In the space-time, this is not compact. It's only compact.
Sure.
So you take the sitter. This is the same as the sitter. This is the picture of the sitter, right? Now, what is the problem with this? Okay, I don't know. Okay. Anyway, coming back here, I was saying that this part below V3 is completely identical with this part of the black hole if you cut it here. So this is, I'm saying that you have something that to you looks like a black hole. And here you can weight like 10 to the 10 to the 10,000 times the age of the universe, right? And this will look to you like a black hole all that time. But then in the end, there is more mass. This is the things with black holes. They are global, you know, so you can play with them. And then this is not going to be a black hole anymore. And there is not going to be future non-infinity, and there is not going to be an event horizon. So this is why I call this thing the frustrated event horizon, because it wanted to be an event horizon, but eventually it will find some more mass, which destroys this character. And again, you have a future singularity. So this is like an enormous gravitational field that somehow swallows the external part of the space-time, and it makes it into a collapsing universe with a future singularity. Of course, this future singularity is just the manifestation that something is going wrong, and that there are particles that end up in a future, in a finite time. Okay, so these are the toy models. Yes. Or can you repeat? You mean in this case? The event horizon here, this is determined by the final mass mu. So this part here is actually the sitter or Cutler. So you know what here the killing horizons, and this is one of them is going to be the event horizon. Yes, but not everywhere. This is only when you are in vacuum or things like that. Yes, so it is in this case this is foliated by marginal top surfaces here, but not there, or not here. And this is also some very well known. In this particular one, yes, the marginally. So now I'm talking about round spheres because there are many marginally trapped surfaces here, but only for the marginally trapped round spheres. They are here, there, and also here, there, and there. And they are different. Some of them are to the future and some of them are to the past. Okay. The same here. Here, there are marginally trapped surfaces only along this line. I mean, round trapped spheres, and no anywhere else. So this red means that these are trapped everywhere. For those of you who know about Kantowski-Sachs models, this is like a Kantowski-Sachs model here. This is a collapsing universe. Okay. So, and then I can also show you another toy model. I don't know if I will arrive at the end, but okay. This is even more interesting because this is a black hole which is already formed. So this is the standard collapse in all textbooks. It's Oppenheimer-Snyder collapse, but now with lambda. So we take a closed Robertson-Walker model. So this is closed. This is the three-sphere metric. scale factor. And if you take the pressure equals to 0, the Friedman-Lemaitre equation looks like this, which, by the way, you may compare with the G00 of the Schwarzschild-De Sitter metric. This is a constant which represents the minimum value of the mass density, and then you are going to match this to Cutler, so to Schwarzschild-De Sitter. And this matches in these coordinates for a chi equals constant, and on the coordinates on the outside at this thing, which is actually a timelike geodesic of the space-time. And now the matching requires some conditions which are obvious. So like the total mass is going to be 4 pi over 3 the density r cubed. Now, assume that this is the case. This is the normal situation. So this is collapse of dust that produces a black hole. This is the black hole region. This is the event horizon. And of course, like this is Cutler, there is also scribe plus here, and this region, which is like the Sitter asymptotical region. So this is the standard situation. And then, look, this is Cutler. I can play as before. I can just make the very same matching that I did before here, because this is exactly Cutler. So I am going to cut here and send mass to this thing, which to all of us is just a black hole, okay? And then there is no black hole anymore, you see? This is the same thing, and I cut here, and I put my mass coming here by matching in the standard way as before. And then this now frustrated event horizon becomes a dynamical horizon and emerges with a timelike membrane there. And they merge precisely at this distinguished surface with the maximum area. So these are the examples of what I call ultramassive spacetimes. Okay, so I don't know. Yeah. So now I just want to make some digression that these things are not, that whenever you have something that you can think of as ultramassive spacetime, and I will give you the definition, then these properties are universal. They are always to have these properties. And for that, I need the stability properties of modes. And so the basic notion of the stability along external directions, and I remind you, the external directions are directions in the normal bundle, which point along the mean curvature vector, or in this case, along K. Now, if one of these marginally outer trap surfaces is said to be stable along one of these directions, when you perturb, and then the expansion becomes positive, the expansion which was 0. And well, this stability can be strict if it becomes positive, or just stability if it is non-negative. Now, the underlying scheme is that if you imagine this surface embedded in a, say, space-like hypersurface, then you are going to say that this is stable when you go a little bit outside, and by outside I mean along the mean curvature vector, and then this becomes untrapped. And well, they have some kind of barrier properties, but I am not going to talk about this. So just to be precise, this is my surface. This is the K along the mean curvature vector because this is null. And then the external directions are given like this. And they are always normalized like that. So they look like this. So in a way, they are given by the norm. But they always point along, the pointer is always along this line. And the important thing here is that I am allowing n to be space-like, or space-like, or maybe null along minus L, or even time-like. Okay? So all directions are here, but always towards the shadowed region here. And then there is something called the stability operator, which was proposed by Anderson, Mars, and Simon some time ago. So the idea is that when you do this deformation, this is equals to some operator acting on this function f, and this is the operator. Here, this is the Laplacian. This is a one form, which is defined like this. where V is any tangent vector. This is the Gaussian curvature. This is the covariant derivative, already said. This is the Einstein tensor. And then there is this function W, which is given by that. So I remind you that this is the shear tensor along K. And this, by the way, is positive. So this entire thing is going to be non-negative unless both terms are 0. Okay. So this is an elliptic operator. And you can prove that it has a principal eigenvalue that I'm going to call it lambda n. So it depends. Given in a direction n, you have a principal eigenvalue, lambda n. And then the corresponding eigenfunction is real and it can be chosen to be positive. And then you can prove that the stability of this object is ruled by the principal eigenvalue. So this is stable if the principal eigenvalue is positive and, sorry, non-negative, and strictly stable if it is positive. Right, there is another way of writing this fundamental thing. If your function is positive, you can compute this, and then you get that this is like that. This is very simple calculation. Now, if you plug here the principal eigenfunction, then you immediately come, this is lambda n, and then you get that. And now take this expression and integrate on your compact surface. So this integrates to 0, and this also integrates to 0. But this term is positive. This term is positive due to the dominant energy condition. And as long as this is a space-like or null, this is also going to be non-negative. And when you integrate the Gaussian curvature, this using Gauss-Bonnet will give you that. So this is where you get the limit for the area. In particular, you get that, but you get many more things. And this is a list of things that you can get here. So this is always the case if your n is non-time-like. And equality requires all these properties. This 0, this is 0, and this has to be like that. In particular, if this is stable along one of these ends, this happens. And also lambda has to be 0, and plus that. And you know that S cannot be stable. It should be stable here in external directions, which are non-time-like, if lambda is positive and the genus is greater than 0. So this is only for spheres now. There are some more cases, but I don't have much time, so I just want to insist that if the area is 4 pi over lambda and this is stable along one end that is non-time-like, then this is symmetric with constant curvature, lambda. And you know that the energy momentum tensor there has to be like this, plus this property. And in particular, this B and C have to vanish if n is a space-like, or if you are in the zone where, sorry, I forgot to say that, this is the zone where the W vanishes. And then there is the area law. And well, I guess you are experts, but if this is the volume or the area forming your surface, and you take the variation along any vector field psi, then you are going to get this formula. This is, of course, what the mean curvature vector does. Here, this is the point, the part of psi which is tangent to the surface. In particular, the variation of the total area is just given by that. This is a standard formula in differential geometry. Now, only the normal part enters here. So remember that we are using these external directions. And these external directions, recalling that my mean curvature vector is like this, when you multiply these two things, they give you this. So if they are marginally trapped, this has a sign. In particular, the area is always to be increasing because theta is negative. And this is the area law. If you follow one of these marginally trapped surfaces along external directions, the area never decreases. And then I don't know if I have some. Okay, thank you. So this is my formal definition of ultramassive spacetime. I call ultramassive spacetime if any spacetime that contains a dynamical horizon foliated by marginally trapped surfaces that have the following properties. All of them are such that this set is not the entire S. So this is the same as saying that W, the function W on this function on these surfaces, is not identically zero. This is the generality condition. And the other thing is that you take any positive epsilon, and then some of the foliated imaginary type surfaces have areas which are larger than 4 pi over lambda minus epsilon. So this I'm saying that I want that these areas go to the limit, keeping the property that they are stable in space-like directions. Okay, so if you have one of these guys, then you can prove all these results. So as you know, there is this parameter S, which was from 0 to tau. So the original S0 belongs to one of these generalized holographic screens that satisfies the area law. The topology is always R cross S2, so they are round spheres. Sorry, they are spheres. There is a distinguished imaginary type surface that I call S bar, which has constant Gaussian curvature k equals to lambda, and therefore the maximum area. And the energy momentum tensor takes the form that I showed you a couple of slides before. Now, any marginal trap tube or generalized holographic screen that passes through S0 is going to change signature somewhere at this distinguished S bar. And at least one of those is going to be null everywhere on this distinguished S bar. And all of these generalized holographic screens become timelike when you go to the past and continue all along the past towards without end, as long as your foliated surfaces keep being marginally trapped with non-zero W, non-identical zero W. So these are the properties that we had in the toy models, but I am not assuming here spherical symmetry. I'm not assuming any form of the energy momentum tensor. Rather, I am getting a form for the energy momentum tensor at the distinguished surface. In this sense, this might be called universal properties or maybe uniqueness properties, I don't know. And there are some interesting, well, this is the proof, but I don't have time. If you are interested, I can give you some hints. But there are some interesting corollaries here. First, this distinguished surface does not contain any electromagnetic charge. This you can prove because of the form of the energy momentum tensor. So there is no electric charge inside this particular imaginary type surface. I mean, this is a round sphere, right? It has constant Gaussian curvature. So you have Killing vectors there inside that. With those Killing vectors, you can compute angular momenta. And all angular momenta that you compute are going to be zero also there. You can prove that very easily. And then, of course, standard singularity theorems prove the existence of a future singularity in the sense of null incompleteness or timelike incompleteness to the future. And there are many ways you can do that. For example, if you assume that there is a Cauchy hypersurface which is non-compact outside the external part, so outside the S bar. So you take a hypersurface which goes through S bar, it's a Cauchy hypersurface. In the external part is non-compact, then you have theorem. And there are many other possibilities. Now, and this is my last slide. Now, I just want to insist on one thing. These things only exist if lambda is positive. If lambda is zero, they are not there at all, okay? And this is very easily proven. Now, they are stronger, they are more powerful than black holes, so they are interesting in this sense. There are many puzzling questions. For example, if you want to do some semi-classical gravity, what happens with Hawking radiation? Where does it come from? Hawking radiation is usually given on the event horizon. There is no event horizon here. Also, there are some problems if you want to do it on the dynamical horizon. Now, I wonder if there is an absolute maximal area for imaginary trap surfaces if lambda is positive, because I could never find anyone which was bigger than 3 over the square root of lambda. In the toy models, the singularity is universal. So this is for all possible observers. I conjecture that this is also true in general, but I have no proof. And these results may have implications for black holes mergers or things So you have a very, very big black hole. And then you send more mass. This is when something funny is going to happen, right? But this is also the case if you have two very, very big black holes that are going to merge. Or if you have a black hole that is eating matter from the surroundings, like the, the accretion disk or things like that. And now, one thing I never spoke is that if you take the diagrams and you put it upside down, you have a version which is the time reversals, and they are also very interesting. But I didn't talk about that. So this is all. Thank you very much.